Alright, we're going to talk about exponential functions first to start off this video, and then we're going to get into inverse functions and logarithms. So, exponentials. So exponentials is really a term I use to describe some sort of raising to a power or combinations of it. And there's a couple rules when dealing with exponents in mathematics, and I'm going to go through a couple of these. So the first rule is if you have some variable and you raise it to a power, let's say you square it, and you want to multiply by the same variable with a different power. So we'll say x to the first power, which is just x. What you do in this case is you just add the exponents. So in this case, you have x squared times x raised to the 1, or many times it's just written by x because the 1 is implied, and you get x cubed. Now you should note that you cannot do this if it's a subtraction or an addition. This rule only applies when it's multiplication, that you add the exponents, or if it's a division, you subtract. So dividing, we're going to subtract 2 from 1, and we'll just be left with x, or x to the 1. But if you do have some addition or subtraction, it just simply can't be simplified anymore. So that's one rule. What if we raise a variable that has an exponent to another power? So instead of just having x squared, we're having x squared and the entire thing is raised to the power of 3, for instance. So x squared cubed. In this case, we multiply the exponents. So in this case, this is going to equal x to the 6, because 3 times 2 is 6. And this works if we take the square root as well, or take some type of a root. So the square root is also written as, or it's the same thing to write it as raising something to the power of 1/2. And this rule applies as well, so you still have to multiply it. So x squared raised to the power of 1/2 is x to the 2 over 2, or x to the 1, or x. Those are really the two main rules that we're going to use for exponents, and I'm going to do a couple practice problems just to get us into the flow of dealing with exponents. So let's do a simplification of what I have written down: 3 to the 4th divided by 9 to the 8th. So 3, I'm actually going to use some different colors for this one. So we're going to simplify 3 raised to the power of 4 divided by, and we'll do different color for 9. So 9, sorry, I get my colors confused, 9 to the 8th. So you might ask, how are you going to simplify this? Especially when this base here, this 3, is different from the base here, which is 9. And you can actually simplify this by going backwards with one of the rules we did before. So this 9 under here can actually be written as 3 squared, because 3 times 3 is 9. So this can be written as the same thing that we had before, so 3 raised to the power of 4, divided by, I'm going to put this in parentheses, so we're still raising 9 to the power of 8, but inside of this, we're going to write 9 as 3 squared. And so to simplify this further, we can carry out this rule here, and we can get something with the same base. So I know I went kind of 0 to 100 here, but just bear with me. So now we're left with 3 to the 4th, divided by, and then 3 to the 2 times 8 is 3 to the 16. 3 to the 16. And now we can do our last simplification. So like I said before, if you divide two powers from each other, you have to subtract. So here we have 4 minus 16. And we're left with 3 raised to the power of 12. Or minus 12, excuse me. 3 to the power of minus 12, which is the same thing as 1 over, I used too many colors here, 1 over 3 to the 12. Whenever there's a negative sign in the exponent, it's the same as 1 over 3 to the same exponent without the negative sign. Let's see, my computer went off. Okay, so we'll do another example problem. I know that was kind of 0 to 100 with the rules, but a lot of these problems are very similar. So we're just going to do a couple more problems just to get in the hang of it. So the next one I had was simplifying a raised to the power of 5 divided by the square root of a. So a raised to the power of 5 divided by the square root of a. And notice I'm using a letter here instead of a number, and that's because these rules apply to any number here and whatever we put in as the base. So I just put a just to represent any number. So to start off here, the way I would solve this is I would first rewrite the denominator that has a square root as a power instead of just the square root symbol. So I would rewrite this as a to the 5th divided by a to the 1/2. And we can use the same rule that we did before, since we have a base raised to a power divided by the same base raised to another power, we have to subtract them. This is going to equal a to the 5 minus 1/2, which equals a to the 4.5. So I guess we'll have to work with this fraction. So 5 is actually 10 over 2. So now we can do the subtraction. 10 minus 1 is 9. So a to the 9/2. And that's our most simplified form in this case. Alright, and the last one I wanted to do is x to the y squared divided by x squared. So in this case, I'm going to use colors again. So this is going to be x raised to the power of y. And all of this is going to be squared. Divided by, what did I say? X squared. That's divided by x squared. Alright, so we'll start on the top this time, and we'll see that we have something in parentheses raised to a power of 2. So in this case we can multiply it, so x to the y times 2 is x to the 2y. So x to the 2y divided by, and same thing here, x squared. X squared. Alright, so we have the same base in the denominator as we have in the numerator, or denominator, numerator, and different values of exponents. So we'll do the rule and we'll subtract it. We'll be left with x, the 2y minus 2. I guess I should write that in purple again. So x to the 2y minus 2. And if you really wanted to, you could simplify this one more step and say that this is equal to x to the 2 times y minus 1. So we could take that 2 out and just do one more simplification. But that is your answer. That's the most simplified it can be in this case without knowing the value of y. But these rules work with letters when you put variables in terms of, or in place of numbers. So yeah, just keep in mind, don't get fooled with undefined variables in these rules. The rules still apply. Alright. And now we're going to move on to inverse functions and logarithms. So, inverse functions. So I know I talked a little bit about inverting a function in the last video. Some of those functions, if you inverted them, you could create a similar line, or whatever the function is, you'd be transposing it or mirroring it across the y equals x line. But right now we're not going to talk about what it really represents in terms of mathematics. We're just going to practice inverting the functions. So inverting the functions is accomplished by just switching the variables of x and y, or x and f of x. So I'll do the first example problem is a simple parabola, so y equals 3x squared plus 7. Alright, so first step in inverting this function is to switch y and x. So I guess I'll write the steps here. So step 1, Step 1 is going to be switching, so switch y and x. So I'm going to draw y and x in different colors on the next line. So we'll say x is green, and we'll put it in the place of y. We'll say x is equal to 3y squared plus 7. And then step 2 is going to be solve for y. And solve for y, we just manipulate the equation until we get y by itself. So I'm going to do that now. For x, we're going to subtract 7 from each side. I'm taking 7 away from x and 7 away from 3y squared plus 7, and we'll get x minus 7 equals 3y squared. And now we'll get the y squared by itself by dividing both sides by 3. We're left with x minus 7 divided by 3 equals y squared. And the last step, we'll take the square root of each side by raising to a power of 1/2. And we are left with, I didn't write x in green there. So we are left with x minus 7 over 3 to the 1/2 equals y. I did it again. And that's our answer. That is the inverse of this parabola that we started with. So let's do 2 more examples with this. Just to get some practice. So now we're going to do y equals the square root of x minus 2 plus 2. Y equals the square root of x minus 2 plus 2. So I'm going to rewrite this and get the square root, rewrite the square root as raised to the power of 1/2. So y equals x minus 2 to the 1/2 plus 2. And sorry, I'll draw x as green and y as red. And so I did this step preliminarily before I went into the steps, just because it's a lot easier working with powers of fractions instead of always dealing with square roots or cube roots. Sometimes you could get a really weird root, like the root of 5/3 or something. It's just easier to use fractions in the exponent. Okay, so step 1, switch y and x. So we're going to do that now. We'll rewrite this as x equals y minus 2 to the 1/2 plus 2. We'll get this block by itself, because we can't add anything or take anything out of this square root because it's inside the power. So really the only thing we can do first is just move the plus 2 to the other side. So we get x minus 2 equals y minus 2 to the 1/2. Now to get this by itself, we have to square both sides to get rid of this 1/2. Remember the rule of exponents, where you multiply the exponents if you have an exponent within an exponent. So in order to get this by itself, that's why we raise everything to the power of 2. And now we can multiply 2 and 1/2. The 2's cancel out, and that gives us just 1. So that's why we're doing that, to get rid of the 1/2. We are left with x minus 2 squared equals y minus 2. And the last step, we can get y by itself by adding 2 to both sides. So we get y equals x minus 2 squared plus 2. Sorry, I kind of ran out of room there at the end. Equals y. And that's our answer. That is the inverse of this function that we started with. Alright, we'll do one more example and then move on to logarithms. The last example I had was y equals x squared minus 4x plus 4. Y equals x squared minus 4x plus 4. So this one will be a little trickier because we have 2 x's on the right hand side to start with. So we'll have to do a trick to get that down to just 1 while we're solving. So step 1, switch y and x. So I'll do x equals y squared minus 4y plus 4. Alright, so to solve for y in step 2, we need to do something to this right hand side so that we can get an expression of this in terms of just one y, instead of having a y squared term and a y to the 1 term. So to do this, I'm actually going to do a little trick. And I notice that there's a positive 4 here and a negative 4 here. So this can be rewritten as a square in itself. So on the left hand side, we'll still keep x. And then I'm going to write this as a square. You can't always do this with a polynomial, but there are some special ones that you can, or special classes of ones that you can. Or I should say, you can't always do this easily. This one, it turns out to be really nice. But to figure out what this is going to equal here in this blank spot, we're going to start with a y, and then we're going to figure out what we want to add or subtract here to get this portion up here. So I know it's going to be a 2, because when we FOIL this out, when we expand this, we know that we're going to be adding something on this side to get minus 4, and adding something, or multiplying that same thing to get plus 4. So in this case, it's going to be minus 2. So that way, I'll just do the expansion here just so you see it. So if we expand this, if we're squaring it, we're going to multiply it by itself 2 times. And then to actually solve this, we multiply the outer ones together to get y squared. We multiply the 2 ones on the left and the 2 ones on the right. We're going to get negative 2 times negative 2, which is positive 4. And then when we have to multiply the left one with the right ones, the right one and then the right one with the left one, we get y times negative 2 is negative 2y. So that's half of this, and then we get negative 2 times y to get the other half. Sometimes it's visualized like this. Basically, we multiply each one of these terms together and then add everything together, and in the end, we get this. So it's a little background, if that's a little bit of a review, but we're kind of doing the opposite, going backwards with that. But we rewrite this, as the square. So now we can solve this for y, because we only have one term. So on the right-hand side, we're going to raise this to the power of 1/2 to get rid of the square term. And whatever we do on the right-hand side, we have to do it on the left-hand side. And we're left with x to the 1/2 equals y minus 2. And with one more step, we have y by itself. So last step, y equals x to the 1/2 plus 2. And that is the inverse of this polynomial. Alright, and now the last part of the video, we're going to do a quick review of logarithms. I know a lot of people do not like logarithms, and I didn't for a while, and now they're alright, but they come up quite a lot. So, logarithms. And let's see. For logarithms, alright, I'm going to start out with the definition of a logarithm. So, logarithms come up when you have an equation that has the variable in the exponent, and you want to figure out what that variable is. So let's say we have 10 raised to the power of x equals 100. Now how do we get x by itself if we want to solve this equation? To do that, we take the logarithm of both sides. Log, in this case, since the base is 10, we say we're taking the log base 10 of this side of the function. And since we do, whatever we do to one side, we have to do the other side. So log base 10 of 100. And again, the whole purpose of logarithms is to try to get the exponent by itself. So in this case, one of the main rules of exponents, and logarithms, and we'll go into more of these rules a little bit later in the video, but one of the rules of logarithms in this case is you can move the exponent down and multiply it to the front. So this is going to be equivalent to this. X times log base 10 of 10. Those two things are equivalent. And now, I know you probably don't know this yet if you haven't used logarithms in a while, but log base 10 of 10, if these bases are the same, this goes away. This is just 1, just a value of 1. So x equals, and then really the same thing we did on the left-hand side, we could do to the right-hand side. If we rewrite 100 as 10 squared, we could bring the 2 down to the front and cancel this out. And you would get x equals 2. And going into it, you probably knew that 10 squared is 100, so that might have been obvious. But in cases where that is not obvious, logarithms can be vitally important. And when the base is not the same as what's on the inside, you just need to use a calculator. If you can't get it to a point where it is equal to the inside, Just use a graphing calculator or something to get an idea of what the value is equal to. So that's the general idea of logarithms, is just having some crazy function with a variable and exponent, and you're trying to get it by itself. So now, logarithm rules. Let me go over a couple rules. So we saw the first rule is when you have a logarithm of some value that has an exponent in it. So we'll say we'll call it log base a, just because it can be the base of anything. We'll keep that same base so that it cancels out. But log base a of some value raised to the power of b is equal to b times log base a of a. A could be anything. This doesn't necessarily have to be a, but if this is the case, log base a of a cancels out. So you could also just say log a to the b equals b. Let me write it in a little bit more generalized form, just because this won't always occur. And we'll say the first rule is log. I'll just leave the base empty because the base could be, this works for any log of any base. So log of a to the b equals b log of a. So that's the first rule. We can move exponents inside the logarithm out to the front. The second rule is when you have additions or subtractions on the inside. So if we have log of x minus y, actually I'll start with additions. Log of x plus y is equal to log of x times log of y, and vice versa. So when you simplify logarithms, you can move two logarithms into a single logarithm. You can fuse it together just by following this rule. Or you can go the opposite direction. You could split it up by taking one of these out of the inside of the logarithm, and as long as you keep the same base, you can split it up and turn it into a multiplication. Now if you have x minus y, I just stopped using the color scheme. Let me add the colors back. So we'll say x plus y. This is x. This is y. Alright. So let's say you have x minus y. This is going to equal log of x, kind of like in the multiplication example, divided by log of y. Right. So same as above, you can turn fractions into a single logarithm or vice versa. Alright, and this will work with any type of logarithm, whatever base you're using. Another important logarithm that often comes up in mathematics and physics is the natural log. So before we talked about equations with base 10, or you could do base 5 or base whatever you want. You can do base pi. Interesting things happen when you use base e. So if you don't remember that value of e, you can look it up. I don't even remember it off the top of my head, but it's 2 something, 2 point something. maybe it's 1 point something, I don't know, but value of e comes up a lot in math and physics. And when you use it as a base to get rid of it, instead of saying log base e, we can just say natural log, ln. So ln kind of undoes e being raised to a power. So similar to what we said before, if you have log base 10 of 10, this equals 1, the same thing happens with natural log. So natural log of e is also equal to 1, because natural log is the same base. It's log base e. And there's some online calculators that will automatically assume when you type in log that you're talking about natural log or log base e, just because of how common it is in problems and really the physical world. So just be mindful of that when you're typing in log into Wolfram Alpha or a program like that. Just make sure that you specify what base you're using when you type in equations to find the answers. Let's see, another identity to use. Yeah, that's really all that we need to do right now. So let's get into some of the practice. We're going to first simplify 3 expressions. So we'll start with log base 3 of 27. So first thing we notice is this is not raised to a power, and the base of the log is not the same as what's inside. So we're going to have to change this number here to get the same base to simplify it. So 27 is the same as 9 times 3. Which, well, yeah, 9 times 3 is the same thing as 3 cubed. So just to double check, 3 times 3 is 9, times 3 is 27. So this is the case. 27 is equivalent to 3 cubed. So this is going to equal log base 3 of, so I guess it's not technically equivalent. There we go. This log base 3 of 27 is the same as log base 3 of 3 to the 3 to the third. So this is going to be equal to 3. No, keep the bases. 3 to the third. Log base 3 of 3 to the third. With our logarithm rules, we know that we can move a power down to the front. So I'm going to rewrite this as 3 times log base 3 of 3. And now we have the same base as we have what's inside the logarithm. This just becomes 1. And we simplify this to a value of 3. Alright, the second example we're going to do is log base 10 of 100, which we already did. So I'm not going to do that again. Third example is natural log of e to the 4th. Natural log of e to the 4th. So this one's pretty simple. We have an exponent, so we'll just move it out to the front. We'll get 4 natural log of e. And like we learned previously, natural log is the same thing as log base e. So the base is the same as what's on the inside. This again cancels out, and we're left with just 4. And that's our answer. Alright, next I'm going to do a couple application problems. So we solved some things. Now we're going to actually solve an equation. So let's do e to the 2x. E to the 2x plus 3 equals 11. Alright, so this looks like it would be really hard to solve with normal algebra without logarithms. We're going to have to use logarithms, so let's get to it. So first thing, I'm going to move this 3 to the other side. We're going to get e to the 2x is equal to 8. Alright, so now we're left with some type of exponent on the left-hand side and just 8 on the right-hand side. So to get this 2x down out of the exponent, we're going to take the natural log of both sides. And we're left with 2x natural log of e equals natural log of 8. Now natural log of e can cancel out. We're left with 2x equals natural log of 8, or x equals 1/2 natural log of 8. If you put this in a calculator, you'd get a value for natural log of 8. I don't know what it is off the top of my head, but that's the most simplified form we can get it in before we need a calculator. Alright, next problem, we're going to do natural log of 3x equals 1. Alright, so in this case, no exponent, not really much you can do here, but we can raise both sides to the power of e to get rid of the natural log. This is something I should have mentioned earlier as well, just like taking the natural log, or little sidebar here, so log base 10 of 10 will cancel it out, same thing as 10 to the power of log base 10. So raising it to the power of the log base also cancels things out, and you get the variable by itself. So it works both ways. So in this case, since we started out with a natural log, we're raising the entire thing to the power of e to cancel this out. And we were left with 3x equals e raised to the power of 1, which is just e. And then we get x equals e over 3. And to get a decimal approximation, again, we can plug that into a calculator. Alright, and let's see. Last one I want to do is, this is quite an involved one. So 3e raised to the power of x to the e. And this is going to equal 27e. Alright, so we'll start off by getting rid of this 3 on the left-hand side. So I'm going to divide both sides by 3. We'll get e to the x to the e equals 9e. Now to bring the x to the e down, I'm going to take the natural log of both sides. And this natural log and this e will cancel, and we'll be left with x to the e equals natural log of 9e. And one more step, you've got to get e to the exponent away, so we're going to raise this to the power of 1 divided by e. Same thing to this side, 1 divided by e. And we're left with x equals natural log 9e power of 1 over e. And if you wanted to simplify this, we could do one more step. So I'll do that up here. So simplifying natural log of 9 to the e raised to the 1 over e. So if you remember our rules with logarithms, if you have two things, oh no, actually I guess we couldn't simplify that. Never mind. We cannot simplify that. So that is the most simplified form in this case. Okay, and let's see. I'll do one last example before I'll end this video. So we're going to do an inequality actually. Is 1 is less than e to the 3x minus 1, which is also less than e. So how do we solve this? We're looking for the range of values for x that will make this true. So to start off, we have to take the natural log of each piece here. The natural log of 1, which I didn't mention earlier, natural log of 1 is going to be 0. The natural log of 1 is 0, is less than, again, we take the natural log of e to the 3x minus 1, so that's just going to be 3x minus 1, because natural log and e cancel out. And then natural log of e is 1. So now we've simplified this to 0 is less than 3x minus 1, which is less than 1. So we're going to add 1 to both sides. So 1 is less than 3x. Less than 2. Divide every side by 3, and we're left with 1/3. So less than x, which is less than 2/3. And that is the range of x values that satisfies this equation. Alright, that is all I have for you today. Next video, we will finally get into limits and then move on to derivatives.